Alright, welcome back ladies and gentlemen. Here in this video we're going to be talking about circular motion, the basics of an object moving in a circle. And for our purposes here, we're looking at an object moving at a constant speed as it travels through a circular pathway. I want to start out by mentioning Newton's laws again. According to Newton's laws, what we know is that if there is no net force, so zero net force, will lead to or result in zero acceleration. And so this is going to be telling us, well, not only will speed be constant, direction must also be constant. Direction. Both of these must be realized. And the reason is, of course, well, an acceleration is a change in velocity, the rate of change of velocity specifically. Velocity has both a magnitude or quantity, that's your speed, and the direction. So keep this in mind. In other words, what we're saying is, since that's something moving in a circle actually is continually changing direction, even though speed might be constant, then it must be accelerating, and therefore there must be a force acting on it. So if we can imagine, I don't know how to draw, so you're going to give me the benefit of the doubt here, finger, 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 and so we got a hand holding on to a string, and on the end of the string we have some sort of ball. That is a terrible looking hand, isn't it? I'm sorry, but you get the idea. And I'm just going to twirl it around and create that circular motion. So we can imagine that. Now, in order to do this, you have to realize that there must be a force acting on this object. Here's the object that we're going to be talking about. These arrows don't represent anything in terms of physics. I'm just pointing out that's the thing we are concerned with, not the hand, and actually not the source of the force that we're going to be talking about either. We'll get into that later on. So the idea here is to make this object move in this circular pathway with constant speed. I'm going to be emphasizing that. Then this force has to exist, and the force actually must be directed toward the center of the circle. There's some force here acting toward the center of the circle. And this is interesting because when the object is located here in the pathway, as it's moving around the circle, that force actually ends up changing direction. In one sense, it's still pointed at the same place, the center of that circle. But in another sense, of course, you can see those two arrows are pointing in different directions. So there has been a change in the direction of the force. As there has been a change in the direction of motion, you can clearly see in this initial position right here, the velocity is in a direction tangential to the circle, and here the velocity is also in a direction tangential to the circle. We're kind of looking at the circle sort of at an angle with a bit of perspective, so it's not a true circle. And then it's also why you might notice something with the angle here. It sort of appears we have a right angle between the force and that velocity vector. And here it kind of appears we do not have that right angle, but if we were to take this and tilt that circle and actually see a circle, we would see this sort of resolve into a right angle there as well. Now, this is really important idea, that this force must exist to produce the circular pathway.
Mr. Digton, please dial extension 4751. Mr. Digton, please dial extension 4751.
Sorry for that. I'm in my classroom and they're doing some announcements from time to time. So I want you to think back. It's been a while since we looked at this. We checked out acceleration vectors, which was section 3-5. That's chapter 3. It's been a while since we were in that chapter. But what it was talking about was the vector nature of acceleration and how that applies to an object moving in a circle. So they gave us this this circular pathway, more or less. And if we imagine a coordinate system with the origin of the coordinate system located in the center of the circle, that's going to be very convenient for us much of the time. So I'll just say x and y. And I'm going to identify location. In the textbook in chapter 3, they were talking about, I think it was a car moving around on a circular track. So if I imagine the car here at one moment, it has a velocity vector in this direction. And sometime later, the car would be here, and it has a velocity vector now in this direction when it's at that location. So we can see that, I should do a velocity there. I should also mark that this would be an initial, this would be a final, if I'm going to compare those two, right? And what I have to realize is that even if the speed around this circular track is constant speed, the values of the velocities is not changing. The value is not changing. The direction clearly is. And when there's any kind of change in velocity, we must be experiencing an acceleration, and therefore there must be some force producing it. So, if we can imagine, I'm going to switch up colors here. I'll go green just because. I'm going to imagine drawing or duplicating this vector here, and what I can see then is from initial to final is the change in velocity that we have experienced, or that this object has experienced. And notice, if I've drawn it carefully, this delta v, this change in velocity, is pointing toward the center of the circle. Now, it's not so intuitive. You might think, well, it's never headed toward the center of the circle. And of course, you're right. But that is nevertheless, that is the direction of the change in its velocity. And if you were to take this a step further and say, well, what about when it's down here? It's now headed in this direction. There's our velocity. And if this is our final, now, and we're going to ignore that intermediate step. Oh, there's a bell for us. Then if I were to take that and superimpose it here, okay, then I would have a different delta v, and therefore there'd be a different net acceleration and so on. So it kind of depends on how you're viewing this. So let's look at this in a little more detail so that we can clearly understand the basic idea here. We have a circular pathway, and we will add our coordinate system just for convenience. So the thing that we noticed was, I'm going to try to be consistent with the colors here that I use, so I'll use green for velocity vectors. We have an initial velocity there. We have a final velocity there. And therefore, we have a delta v. I'll superimpose that final velocity here, and we saw the delta v here. I'll change the style of the arrowhead so it stands out a little bit. Delta v. It is important to note the direction of that change in velocity. And the reason is, the direction of the acceleration. And therefore, the direction of the net force must point in the direction of the delta v. It must. They must point in the direction of delta V. They do. There's no other way about it. And we know that this is going to be toward the center of the circle. There's no change in speed, and it results in that sort of arrangement. So that's the implication here, that the acceleration vector and the net force vector both also are aimed or point toward the center of the circle. Now, this is important to realize. This is just assuming a constant speed. That condition must exist. If we're varying the speed, then this no longer holds true right here, right? There would be some other direction for the net force, and therefore also for the acceleration. We're not going to deal with that right now. Let's keep the speed constant, and we're going to be able to do some really cool things with this. Okay. Video continues. I want you to close your eyes for just a moment. I'm not going to draw anything or write anything for just a moment. I'd like you to think about your own personal experiences, particularly in a car. Have you ever noticed that as the car makes a turn, let's say you're headed north and you want to turn right, and so you'll be headed east at that point, that you're going to go through this turn. Well, the faster you go through that turn, the harder you seem to push against the door of the car, right? The slower you go, the less you push against the door of the car. And it's kind of an interesting thing. We've all experienced something like that before. A different experience you may have noticed, this one may not be quite as obvious, but if you're driving, if you're in control of the speed of the car, it may be a little more likely that you've noticed this. You're driving at a given speed, right? And you turn the steering wheel to make a turn. If you turn sharper at that speed, then you're also thrown into the door of the car harder, right? In other words, by turning the steering wheel more, you're making a sharper turn. What you're really doing is you're turning along a circular pathway that has a smaller radius. So a smaller turning radius there. And so keep that in mind. So if your speed is constant and you turn the steering wheel just a little bit, it barely throws you against the door. If you turn your steering wheel dramatically, you get thrown against the door of the car. You have experienced this. You can notice the next time you're in a car. Just don't do anything crazy and get hurt, please. Well, those sensations, getting pulled toward the door of the car, they're sort of misleading. So we'll get to that. But that outward pull that you seem to experience is misleading. But you know what? So is the sensation of being pushed up by the ground. If you think about that, well, the ground is holding you up, yes, but what is it that's really happening to you? That upward push is really a reaction to the downward pull of gravity. So we're going to see that a similar sort of thing is happening with forces and accelerations when an object moves through a circular pathway, like a car during a turn. Okay. Now, if you're doing that, we mentioned heading north, and then you're going to go make a turn and head east, right? So, in the first case, we were talking about different speeds. So you go faster, you have an initial velocity through this turn, or you have a faster velocity through this turn. Then what you're going to notice is with the faster velocity, you feel like you're thrown out away from the turn more, right? Well, in the second example or sort of scenario that you may have experienced, we were talking about changing how sharply you turn the car. So if you have a constant velocity, and this is you're just driving along, and you turn the wheel gently, you make this nice wide turn. Well, that's going to be a different experience to you in the car compared to getting the same direction with a much sharper turn like this, right? Really what's happening here is we're taking this and there is a radius there. right? This turn, this part of the turn, is part of a circle, and we have a circular pathway. There's a radius to every circle. Now, the difference here that you want to pay attention to is the circle here is much smaller, and you notice that radius is much shorter. And what you experience is, with the larger radius for that given speed, you don't seem to be pushed against the door of the car very much. But at that same speed, with a tighter turn, you get thrown against the door of the car pretty violently. And so there's a couple things to note from this. It seems that the resulting effect on you is related to two things. It's related to your speed through the circle. Faster means there's a bigger effect, you notice. And also it's related to the size of the circle that makes up the pathway. A smaller radius in that circle is going to have a more dramatic effect on you. And excuse me. So it seems like it's that this must be related to both speed and size of the circle. And it turns out that it's a very special thing that often is not mentioned in pop culture or movies and whatnot. A physicist wants to talk about this thing called centripetal acceleration. Okay, now you've not heard this term most likely. Most people haven't. Because in movies and whatever else, TV shows, doesn't matter, you're often hearing the term centrifugal force. I'll throw that up here. Centrifugal force. Right, this is what y'all hear. Oh man, the pulling a lot of G's. The pilot in the jet fighter is experiencing 7 G's of force. The driver of the drag race car is experiencing lots of G's, G forces. Well, centrifugal force is kind of a misleading thing. The problem is it's what you feel like is going on. When you're getting thrown, you take the sharp turn, you're getting thrown against the door on the other side, on the outside of the turn, right? You turn right, you feel like you're thrown to the left. Well, you aren't thrown to the left. The thing is, your body has inertia, and it already has a direction of travel, which is that way. And you turn the wheel of the car, and it's the car that actually moves to the right and bumps into you. You don't move to the left and bump into the car moves to the right and bumps into you. And how sharp that turn is can affect how hard the car bumps into you. And then once it makes contact, it can push on you, and you go through around the turn with the car. Same thing's happening here, of course. You go through this nice gentle turn, but you go too fast, and it feels like you're thrown outward, right? You feel like you're being pulled away from the center of the circle, but instead, really, your body's just trying to keep going the way it was going. Newton's first law. Things are going to keep doing what they want to do. And the car will turn and bump into you. So this guy right here that we think we are feeling actually is a force that doesn't exist. Centrifugal force does not exist. It doesn't. It's a myth. The problem is it's what we think is happening because it sure feels like it's there. But it is just your own inertia headed straight when the car is trying to make you turn. That's all that's happening. Now, so what is this business? Well, the centripetal acceleration is the acceleration toward the center of the circle. So I'm going to come back to this real quick. If there's a delta V here, we've already said, look, the acceleration and the net force must be in the direction of that change in velocity. There must be an acceleration toward the center of the circle right there. It absolutely does exist. And that is called centripetal acceleration. Here's the notation that we like to use. ACP for centripetal acceleration. Turns out that it is related to the speed and the radius of the circle. But this relationship is well, it's quite simple, but it's actually very important. And also, remember, constant speed. Okay, this works for constant speed. So if there's a change in this quantity right here as time goes on, then this is not really going to be helpful to you. It's going to be more complicated. But if there is a resulting acceleration, then there must be a force. And that is not called centrifugal force, it's centripetal force. This is what actually exists. This is what physicists talk about. And so you have centripetal force. Well, if your speed is constant as you go through this circle, then the only acceleration you're experiencing is the centripetal acceleration. No other forces acting on you that have any impact on your motion. So this guy is really equal to the net force. And so we just have mass times acceleration, but the acceleration is your centripetal acceleration. So that's it. It's like a rewrite of Newton's second law, but it's Newton's second law as applied to an object moving through a circular pathway at constant speed, right? Okay. So what does this mean for us? And we'll work through an example or two, and we will figure this out. So much of physics is learned through examples. So the first example here, actually I'm stealing this from the textbook. This is going to be page 186, number 105. So that's what I want to look at. So you can reference that question. And essentially what it does, it's kind of an odd setup. It's not a setup you would expect to really really exist and be useful, but let's imagine a table, right? And in the table, in the center, is this hole. Draw some table legs here so we have some more realistic imagery. Now, on the table is a disc-shaped object, maybe like a hockey puck, right? And the hockey puck is a string tied around it, and the string goes to this hole and passes down through the hole and down below. And then to the string is attached a mass, capital M for that mass. And what we need to do is imagine that this hockey puck, if you will, is going to be set in motion around a circular pathway. Right. Remember, this is a circle that's foreshortened, so you're kind of seeing it with some different perspective. So there is a radius, which is the length of that string, because the string essentially goes through the hole, which is the center of that circle. This hockey puck itself has a mass. I'll call that lowercase m. I'll write it down here. And if we set this object in motion, that motion will be a velocity, and I'm going to draw that velocity vector perpendicular to the radius, or in other words, tangential to the circle itself, to that pathway. So in this problem, we're kind of asked to figure out, well, what does this velocity have to be in order for this situation with this mass hanging down below to be like an equilibrium situation. Right? If you get this, and we're imagining the surface of the table is frictionless. Not very realistic, but the whole setup is kind of wacky. How fast must we spin that thing around in a circular path to keep this mass stationary? That's the question. So here's what we're going to do. We're going to set up some interesting things. We'll start here with this mass. We know we have that thing stationary. That's going to be an equilibrium situation. And in equilibrium, the forces are balanced, and what we have is a force of tension pulling up on this thing, plus a force of gravity pulling down, and when you add those together, you have to get zero, right? Well, this is going to be a downward force, so it's kind of like adding a negative. What we get from this is essentially that the force of tension pulling up, and the weight, force of gravity pulling down, which is mg. capital M, sorry. Two M's in this problem. Those are equal and opposite. Brilliant, good. Now, however, let me write that down. Okay. There's something else I need to realize, and that is that I need to recall this string goes up and over this way, and the tension in the string must be the same everywhere. All right. So now, what force could possibly be leading to this object moving in that circular pathway? It's a force that must pull toward the center of the circle, and that would be the tension in the string. So the tension of the string is also equal to the centripetal force that we have. The centripetal force acting on this guy to create that circular motion. Okay. So here I go with my M's again. Capital. Just realized that. Okay. You caught that, I'm sure. So the next step really is I'm going to break this guy down. Lowercase m here, and this is going to be times acceleration centripetal acceleration. And this now is going to be a useful equation right here, because I know that inside the centripetal acceleration is hidden a v, a velocity, and that's what the question wants to know. So I'm going to do a simple rewrite. I'm going to take that guy and borrow him. I'm going to take this term and borrow him and rewrite the a. And so capital M times gravity equals lowercase m times, and now instead of ACP, I'm going to write my c squared divided by r. There we go. And at this point, I simply need to solve for the velocity. And when I do that, rearranging things, I get velocity is equal to the radius times the mass of the large object times acceleration due to gravity divided by the mass of the smaller object, this hockey puck, but this is all going to be inside a radical. And that is it. That is the answer that we needed. We had no numbers, no quantities other than the variables. So that's it for that problem. And you look at it and you go, well, it can't be that simple. Well, it really is in this case. It really is. You had a static situation here. You had a simple circular motion situation here. And the speed here is just enough to maintain that static situation for this object hanging down below the table. And so recognizing this bit becomes real important, okay? And it really just stems from equilibrium. It stems from Newton's second law of motion. Net force equals 0 on this lower object. Okay, I want to look at another example now. And this one is nice because it has us draw a simple diagram, but from a different point of view. We won't see the circle in this example. So another example here. Same page in the textbook. By the way, we're in chapter 6, right? But this time, I want to draw on question number 107. Okay, so in this question, really what we're asked is a couple things. There's a situation where we have an amusement park ride, and the amusement park ride is this big sort of twirly thing, and I don't know, something spins around. So we have this thing rotating, and it's going to be large because down below what you have are these chairs. I don't know how to draw a chair, so forgive me. Maybe there's some sort of thing there, and you sit in the chair and you just kind of, you know, are going around, right? And it's pretty cool. It's a nice chill ride, but we're going to have to diagram this in a way that we don't see the circular pathway. because so we're going to be asked some questions about this. Well, first, if we're given some information about the chair and a passenger perhaps, then we're going to be asked, what is the centripetal acceleration? That's going to be part A. And we're also going to be asked in part B, what is the angle theta that these support chains make with the vertical? And that's where the different perspective is going to come in handy. For this question, I also am going to be asked to explain a kind of an interesting thing that's going to pop up out of this question. So there is a part C, and we're just going to kind of put a question mark there. I'm going to hold off on telling you what it is at the moment. Now, we have some information, but first I want to kind of sketch this out, not looking at the circle. I'm going to imagine myself at eyeball level with the chair, and so from my perspective there, I really wouldn't see a circle. I would see the chair simply go back and forth over and over and over. And a simple sketch of that chair, right? Basically a free body diagram is what I'm looking at. This chair is going to have weight, of course. Okay, so we'll have force due to gravity. And if we ignore air resistance, there's really only one other force that's important, and it's the tension pulling up this way. And let's imagine it's just kind of one singular force. We'll combine all into one singular force of tension. Okay. And so we can see right away, well, of course we have circular motion, so there will be a centripetal acceleration. We have this diagram, which is showing us an angle, and this is going to be one of the questions we need to answer. Angle theta with respect to the vertical. So theta shows up right there. And I'll just kind of do one of these. There's theta, right? So I believe I can get to work as long as I have more information. I need to understand a couple things. There is a radius of the circle, right? And so radius is 12 meters. I am also told that the velocity is a constant speed. Remember, we're going to be dealing with that situation. 25 miles per hour is our speed. So the first thing I want to do is I want to look at the centripetal acceleration and find that. So I have radius, I have velocity. It should be straightforward. However, I don't like these units, so I'll do a conversion, and I will end up getting just about 11.2 meters per second. I'm going to save that work for you. It's very straightforward stuff. So now I have units that jive, and I can get right into a solution. So centripetal acceleration, I know that it is velocity squared, or speed squared, divided by radius. So I have 11.2 meters per second squared, and my radius is 12 meters. And when I do that math, right around close to 10.5, right? Meters per second squared. That's it. That is the centripetal acceleration. The acceleration toward the center of the circle. And it's interesting to note that it's pretty close to the value of g, right? So if g is 9.81 meters per second squared, right? Well, this acceleration toward the center is sort of in that ballpark. And what that means is riders will experience that inward acceleration, but really what they're going to feel is they're going to feel like they're thrown outward, but they're going to feel like they're thrown outward at this rate of acceleration. And so it'll be quite noticeable, enjoyable, not very harsh, but noticeable, and makes it a good ride. But that's it for part A, right? We've answered that question. Check. Now, how about that angle? So let's get started on that. This way, so we can see everything a little better. Go to part B here for that angle theta. So there is an acceleration toward the center of the circle, which, with the way I've drawn this, toward the center of the circle is this way, right? So there must be a net force acting in that direction. So I don't want anything over here canceling it. However, I do want something canceling this downward force of gravity. I need something upward. I don't want any up or down acceleration during the ride. Not for this ride. So there's going to have to be something there, right? And it has to be enough to cancel this. So think about this for just a moment before we continue. The heavier the rider is, let's say you're talking about an adult versus a child. The adult's heavier, larger downward force. There must be this larger upward force to compensate. And that comes from that tension in the cable. So let's work that out, right? So what I have basically here is the Y component. No big deal there. And what I know is that the sum of the forces in the Y direction need to be 0. But those forces are the force of tension in the Y direction, and that's in the positive Y direction, and in the negative Y direction, mg. And when I do that, I should get 0. So, therefore, force of tension times cosine of theta equals mg. And I chose cosine because if I look at the way this triangle is drawn, right, this is the component of tension that I'm looking for, and it happens to be adjacent to theta. So adjacent means cosine. So there's no confusion there. But I have an issue, and the issue is that angle theta is an unknown, but so is Ft, force of tension. I have two unknowns here. So at this moment I cannot solve. However, what I can do is look at the x direction. And when I sum the forces in the x direction, I do not want 0. I need that centripetal acceleration to result. So this is going to be equal to the force of tension in the x direction, and that's it. That's that guy right there. That's it. And that is equal to the mass times the centripetal acceleration, right? Newton's second law happening right here. But this is also the component of tension. Oh, another bell. So that component of tension happens to be the force of tension times the sine of theta. And so, all right, it looks like I have two equations with two unknowns. Except mass is also an unknown, isn't it? We weren't given any mass. I wonder what's possible here. So let me try something here. Let me try. I'm gonna look at this, and I'm thinking, you know what? In this guy, what if I just solve for the force of tension and see where that takes me? Okay, I'm gonna try stuff. That's what you have to do quite often, is simply give something a shot and see where it leads you. When you do this, I'm solving this for force of tension, by the way. What you end up with is mass times centripetal acceleration divided by sine of theta. All right, now I have this unknown in this equation also. So what if I just did a substitution here into that one? And let's see what results. Substitute. And so I'm going to rewrite this, but I'm going to do the substitution right away and see what happens here. All right, and then cosine of theta, and that's going to equal mg. So first things first, right away, mass cancels out. I don't need to know the mass, and that's super convenient. I don't know the mass. But it also should remind you of other situations where mass cancels out. Anytime there's an object accelerating due to gravity, all objects accelerate at the same rate because of gravity, or when it's gravity causing that acceleration. So maybe no surprise, or maybe just kind of an interesting coincidence. But here we go. We're looking for angle theta. We have acceleration toward the center of the circle. We know what g is. We're looking for theta. I've got a sine and a cosine, and in fact, I rearrange this to look like this. Okay. Now, maybe at first glance you don't notice anything. Maybe you do, because what happens here, am I allowed to just flip this? Well, yeah, if I flip this, but I also got to flip the other side too. Take the reciprocal of both sides, and I end up with sine theta over cosine theta times 1 over centripetal acceleration equals 1 over g. And this is kind of cool because this resolves into tangent. And if I multiply both sides by ACP, then that goes over there. See what happened right there? That just resolves. And multiply that. And this is looking pretty awesome, totally solvable. I'm going to say theta is going to be equal to inverse tangent of that business right there. Right? So now I just have to plug in some numbers. And my centripetal acceleration was 10.45 meters per second squared. Keep track of your units, people, please. And g is 9.81 meters per second squared. So this angle, check this out. This is, at this point, maybe worth just mentioning real quick. Angle theta seems to be related to this ratio, the ratio between the centripetal acceleration and g, and related through the tangent function. So what we get when you do this is theta seems to be equal to, depending on how many sig figs you like, 46.8, about 47 degrees. So we've answered that question about our situation also now. So I can come back here and I can go check. All right. Now the last question, part C, question C, was really about mass, and it wants to know how come. What is the role of mass here? What if there was a heavier rider, an adult versus a child? What happens? Does theta change? Does the centripetal acceleration change? And the answer is no. Both weight and the centripetal force, the force which ends up changing the direction of the chair with the rider, they both depend on mass in the same way. And what ends up happening, as we saw here, mass cancels right out. It's gone. It doesn't matter how much the rider weighs. All the chairs will be at the same angle with respect to the vertical. And you can observe this. When you go to an amusement park, you go to Knott's Berry Farm, Magic Mountain, doesn't matter. Look at one of these rides and notice that chairs that have riders and chairs that are empty both sort of make the same angle with the vertical. It doesn't matter whether there's a rider. Some interesting stuff. One last thing for you. One last thing. Okay, so check this out. Bells. I'm hearing bells. Okay, this is going to take just a moment because I'm not doing this one for you. But I want to bring this one up. Question 110. All right. I want you to take a look at this question. And it's a good one. I don't think it's super difficult. Not really. And I just want to give you a hint. Okay? A hint for this question. I want you to draw free body diagrams for each position. There are positions A, B, and C that are illustrated in the question. You'll see what's going on. As soon as you read the question, this is going to make total sense to you. So try to solve question number 110 on your own and do it with this method, okay? And I bet you come up with it. I bet you're going to have not too much difficulty at all. But if you do, let me know. Thanks for watching. See you next time.